Autotransformer starters are addressed in the 1999 National Electrical Code, specifically within Article 430, which covers motors, motor circuits, and controllers. Section 430.72 directly discusses autotransformer starters. Autotransformers, also known as autotransformer compensators, are a type of reduced voltage starter commonly employed for AC induction motors. Understanding their application and code compliance is essential for electrical professionals. To understand autotransformer starters, let's begin with the basics. An autotransformer is a type of transformer that uses only one winding for both the primary and secondary circuits. This single winding is tapped at various points to achieve different voltage levels. Unlike a traditional two-winding transformer, an autotransformer provides a direct electrical connection between the input and output. The fundamental principle behind an autotransformer starter is to reduce the voltage applied to the motor during the starting period. Induction motors draw a high inrush current when initially energized, typically several times their full load current. This high current can cause voltage dips in the power distribution system, potentially affecting other equipment. It also creates significant stress on the motor windings. By using an autotransformer to reduce the starting voltage, the inrush current is correspondingly reduced, mitigating these issues. During starting, the autotransformer is connected between the power source and the motor. The motor receives a reduced voltage, typically 50%, 65%, or 80% of the full line voltage. This lower voltage limits the inrush current. As the motor accelerates and approaches its rated speed, the autotransformer is gradually switched out of the circuit, and the motor receives the full line voltage. There are several advantages to using autotransformer starters. Firstly, they provide a relatively smooth and stepless acceleration compared to other reduced voltage starting methods. Secondly, they offer good starting torque per ampere of line current drawn. Thirdly, they are suitable for applications requiring frequent starts and stops. However, there are also some disadvantages. Autotransformer starters are generally more expensive than other types of reduced voltage starters, such as resistance or reactor starters. They also require more space due to the size of the autotransformer. Now let's dive into the specific requirements outlined in the 1999 National Electrical Code, Article 430, Section 430.72. This section provides guidelines for the proper installation and application of autotransformer starters. The code emphasizes the importance of selecting an autotransformer with an appropriate voltage rating for the motor being started. The voltage rating must be compatible with the available line voltage and the desired reduced voltage levels. Furthermore, the code mandates that the autotransformer be protected against overcurrent. Overcurrent protection devices, such as fuses or circuit breakers, must be installed in the primary circuit of the autotransformer to protect it from damage due to excessive current flow. The overcurrent protection devices should be sized according to the autotransformer's rated current carrying capacity. Additionally, the code requires that the autotransformer starter be equipped with a suitable disconnecting means. The disconnecting means allows the autotransformer and motor circuit to be completely energized for maintenance or repair purposes. The disconnecting means must be readily accessible and capable of being locked in the open position. The 1999 National Electrical Code also addresses the issue of motor overload protection. Motor overload protection devices, such as thermal overload relays, are designed to protect the motor from overheating due to prolonged overcurrent conditions. These devices must be selected and installed in accordance with the code requirements to ensure adequate motor protection. Moreover, Section 430.72 specifies that the autotransformer starter must be installed in a suitable enclosure. The enclosure protects the autotransformer and associated components from environmental factors such as dust, moisture, and physical damage. The enclosure must be rated for the specific environmental conditions in which the autotransformer starter is installed. The code also addresses the grounding requirements for autotransformer starters. The autotransformer and associated equipment must be properly grounded to ensure personnel safety and to minimize the risk of electrical shock. The grounding system must comply with the requirements outlined in Article 250 of the National Electrical Code. In addition to these specific requirements, Section 430.7d2 refers to other relevant sections of Article 430 that may apply to autotransformer starters. These sections cover topics such as motor disconnecting means, motor branch circuit protection, and motor control circuit wiring. It is essential to consult these sections to ensure complete compliance with the code. When selecting an autotransformer starter, it is crucial to consider the specific application requirements. Factors such as the motor's horsepower rating, voltage rating, and load characteristics must be taken into account. The autotransformer starter should be sized appropriately to provide adequate starting torque and to minimize voltage dips in the power distribution system. In addition to the technical requirements, the 1999 National Electrical Code also emphasizes the importance of proper installation practices. The autotransformer starter should be installed by qualified personnel who are familiar with the code requirements and the specific characteristics of the equipment. The installation should be performed in accordance with the manufacturer's instructions and all applicable safety regulations. Regular maintenance is also essential to ensure the continued safe and reliable operation of autotransformer starters. The autotransformer and associated components should be inspected periodically for signs of wear, damage, or corrosion. Any necessary repairs or replacement should be performed promptly to prevent equipment failure. In summary, autotransformer starters are a valuable tool for reducing inrush current during motor starting. The 1999 National Electrical Code, Article 430, Section 430.7d2 provides specific guidelines for the proper installation and application of these starters. By following these guidelines, electrical professionals can ensure the safe and reliable operation of motor control systems. Remember to always consult the latest edition of the National Electrical Code and any applicable local codes or regulations for the most up-to-date requirements. Understanding autotransformer starters also requires an understanding of motor control principles. Motor control involves the techniques and equipment used to start, stop, accelerate, decelerate, and protect electric motors. Autotransformer starters are just one method among many for controlling motors, each with its own set of advantages and disadvantages. Other common motor starting methods include across-the-line starting, resistance starting, reactor starting, pot winding starting, and variable frequency drives, often abbreviated as volts per hertz. Cross-the-line starting is the simplest and most economical method, where the motor is directly connected to the full line voltage. However, it results in the highest inrush current. Resistance and reactor starters use resistors or reactors in series with the motor windings to limit the starting current. These methods are less expensive than autotransformer starters but provide lower starting torque per ampere. Part winding starting involves energizing only a portion of the motor windings during starting, which reduces the inrush current. This method is only applicable to motors specifically designed for part winding starting. Variable frequency drives, or volts per hertz, provide the most sophisticated motor control, allowing for precise adjustment of motor speed and torque. However, they are also the most expensive option. The selection of the appropriate motor starting method depends on various factors, including the motor's size, the load characteristics, the available power distribution system capacity, and the cost constraints. Autotransformer starters are typically used for medium to large size motors where reduced voltage starting is required to minimize voltage dips and mechanical stress. In addition to motor starting methods, motor control also involves the use of various protective devices. These devices are designed to protect the motor from damage due to overload, short circuits, and other abnormal conditions. Common motor protective devices include fuses, circuit breakers, thermal overload relays, and ground fault relays. Fuses and circuit breakers provide overcurrent protection, interrupting the circuit when excessive current flow is detected. Thermal overload relays protect the motor from overheating due to prolonged overcurrent conditions. Ground fault relays detect ground faults, which can cause electrical shock hazards and equipment damage. Motor control circuits also include various control components such as push buttons, selector switches, relays, and contactors. These components are used to control the starting, stopping, and reversing of motors, as well as to provide interlocking and sequencing functions. Push buttons and selector switches are used to manually control the motor operation. Relays and contactors are used to switch electrical circuits and to provide remote control capabilities. The design and implementation of motor control systems require a thorough understanding of electrical principles, motor characteristics, and applicable codes and standards. Electrical engineers, electricians, and other qualified professionals are responsible for ensuring that motor control systems are designed and installed safely and reliably. The National Electrical Code provides comprehensive guidelines for motor control systems, covering topics such as motor disconnecting means, motor branch circuit protection, motor overload protection, and motor control circuit wiring. Compliance with the NEC is essential to ensure the safety of personnel and equipment. In conclusion, understanding autotransformer starters and motor control principles is crucial for electrical professionals. The 1999 National Electrical Code, Article 430, provides detailed requirements for the installation and application of these systems. By adhering to these requirements and employing sound engineering practices, electrical professionals can ensure the safe and reliable operation of motor control systems. It's essential to remember that electrical codes and standards are constantly evolving to reflect advancements in technology and to address emerging safety concerns. Therefore, it's crucial to stay up to date with the latest revisions of the National Electrical Code and any applicable local codes or regulations. Continuous education and professional development are essential for electrical professionals to maintain their competence and to ensure that they are providing the highest level of safety and service. Furthermore, the NEC is not a design manual. It provides minimum safety requirements. Good engineering practice often dictates exceeding these minimums to improve system performance and reliability. Factors like voltage drop, harmonic distortion, and motor efficiency should also be considered in the design process. Understanding these factors can lead to a more robust and energy-efficient motor control system. Consider the specific application of the motor. Is it powering a pump, a fan, a conveyor, or some other type of equipment? The load characteristics of the driven equipment will influence the selection of the appropriate motor starting method and control scheme. For example, a pump may require a soft start to prevent water hammer, while a conveyor may require precise speed control to synchronize with other equipment. Also, remember that safety is paramount. Always follow proper lockout-tagout procedures before working on any electrical equipment. Wear appropriate personal protective equipment, including safety glasses, gloves, and arc-rated clothing. Work in a well-lit and ventilated area. If you are not qualified to work on electrical equipment, seek the assistance of a licensed electrician. Furthermore, consider the environmental conditions in which the motor control system will be installed. Will it be exposed to extreme temperatures, humidity, dust, or corrosive substances? The equipment must be appropriately rated for the specific environmental conditions to ensure long-term reliability. Enclosures should be selected based on the NEMA rating, which indicates their level of protection against various environmental hazards. Proper wiring practices are also essential for a safe and reliable motor control system. Conductors should be sized according to the ampacity requirements of the circuit, and connections should be made using approved methods. All wiring should be neatly organized and supported to prevent damage or strain. Grounding is another critical aspect of electrical safety. The motor control equipment and associated enclosures must be properly grounded to provide a low impedance path for fault current. This helps to minimize the risk of electrical shock and to protect equipment from damage. Grounding conductors should be sized according to the requirements of the NEC, and all connections should be made securely. Finally, remember that documentation is essential for any electrical system. Keep accurate records of all equipment, wiring, and control schemes. This documentation will be invaluable for troubleshooting, maintenance, and future modifications. The documentation should include wiring diagrams, equipment specifications, and operating instructions. By following these best practices, you can ensure that your motor control systems are safe, reliable, and efficient.